Let's continue the latter part of chapter 4. Now we will deal with the example 4.3, 6 special open chain. Okay, here we have the 6 level joint here. 1, 2, 3, 4, 5, 6. Okay, pole kinematics will be written using the space form of the POE. It's very easy. In order to obtain the final transformation matrix, we should know the zero position and the 6 square axis. Okay, let's read the final the zero transformation from here. Okay, this is the fixed frame. This is the base frame. Okay, the x can be led by the same x, so 1, 0, 0. Okay, the y-x is the same, so 0, 1, 0. Z is the same, so we have the identity rotation matrix. Actually, both are same. Okay, let's read the position of base body frame in terms of the space frame. It will be corresponding to L1, L2, L3 in the y direction, so 0, 3L, 0. And then remaining 3, 0, and the 1 is required to make the homogeneous transform. Okay, it must be the zero position. Okay, let's obtain the square axis. Okay. Okay, S1. S1 is about this axis. Maybe this rotation is about the g-axis, so 0, 0, 1 is assigned to the omega 1, and there is no translational movement of this part, so 0, 0, 0 as a linear velocity, S2. Okay, this rotational movement is corresponding to the y-axis, 1, 0, 1. I'm sorry, the 0, 1, 0. And this rotation axis is going through the origin, so we have the 0, 0, 0 linear velocity, and S3. Okay, S3 is corresponding to here. Okay, this is corresponding to minus x, so minus 1, 0, 0. If you are using the right-hand rule, you can know that the minus x direction movement, rotation. Okay, the 0, 0, 0 linear velocity. S4. Okay, this one. This is correspond to the minus x, minus 1, 0, 0. It will, let's assume that this is the turntable. The minus x movement applied to here, at that time the origin will have linear velocity like this, plus g direction with the magnitude of L, so 0, 0, L. Okay, S4, this is very similar to the S5, it's very similar to the S4, so minus 1, 0, 0, 0, 0 to L, because the distance is 2 times. Okay, S6. Okay, this rotation movement is corresponding to the y-axis, so 0, 1, 0. It going through the origin of the base coordinate, so there is no linear velocity. So like this we can obtain the 6 square axis. Okay, let's take another example. It is composed of the R, P, R. We have the linear prismatic actuator in here. Okay, let's read the zero position. The x-axis is corresponding to the x-axis, so same. Y is the same, G is the same, so we have the identity rotation matrix. Okay, here let's read this position in terms of the space plane, okay, the 2L y direction are required. No z, no x, no z. So we have the y directional displacement as L1 plus L2. Okay, the remaining task will be obtaining the square axis. This is the 1, 2, 3, 4, 5, 6 joint. Okay, let's obtain S1. S1 is 0, 0, 1 because this rotation movement is corresponding to the z-axis. It going through the origin, so 0, 0, 0 linear velocity. S2, this is corresponding to x-axis movement 1, 0, 0, and linear velocity will be the 0. S3, the prismatic joint. So in this case, there is no rotation movement. So 0, 0, 0. It is the noted by the prismatic joint. Okay, how about the linear velocity? If you make the some movement like this, at the time the y directional movement appear. So 0, 0, 1, 0. Not L1 because the unit vector is required to either rotation omega and v. So in here, the unit v will be used to describe the square axis according to definition. Okay, as for this one, it is corresponding to y-axis 0, 1, 0. No linear movement. S5. Here, x-axis, and this movement will make the minus g directional linear motion at the origin. So with the magnitude of the L1, so 0, 0, minus L1. S6, the rotation angle will be aligned at 0, 1, 0, and there is no linear movement because the axis is going through the origin. Okay, so 0, 0, 0. Like this, we can make the list of square axis. Okay, this is a more practical example. This UR5 is very famous robot system in the world. Okay, let's consider the board kinematics of the UR5. Okay, the every joints are revolute, and there is a kinematic data. W1 here, maybe the 10 centimeter is about 10 centimeter. Okay, so like this we can get the kinematic data from the website of the UR. Okay, find the fold kinematics at first angle is 0, second angle minus 90 degrees, third and fourth are 0, fifth angle is positive 90 degrees. This value will be applied to the fold kinematics. At that time, the end effector frame will move, will take some posture. That is the problem of this example 4.5. Okay, let's read the configuration of zero position. This is the zero position. Let's read it. Okay, here, its bottom part, x and y and g is aligned as a base frame, and x and y and g is the space body frame. Let's read. Okay, this x-axis is aligned to minus x, so minus 1, 0, 0 appear as a first column of the M matrix. Okay, y, this is y. Y is aligned to z, so 0, 0, 1. Okay, and z-axis is aligned to y, so 0, 1, 0. Okay, the x directional position will be the L1 plus L2 plus. So this is the x position. Y directional movement will be the W1 and plus W2 going forward. And in the case of the Z, H1 is upright and then H2 is going down. So H1 minus H2 appear as a position of final computation. Okay. Okay, so let's obtain the square axis, all the joint. Okay, first one. This is the S1, this is the S2, S3, S4. Where is the S4? S4 is here. S5, S6. Okay, S1. The rotational angle is aligned to the G, so 0, 0, 1. This axis going through the origin of the base frame, so 0, 0, 0, linear velocity appear, S2. Okay, then let's leave. This rotational angle is aligned to the y-axis, 0, 1, 0. And actually, there is some linear distance. So according to the rotational movement, the base angle, the base frame will move like this with the magnitude of the h1. So minus axis with the magnitude h1 and the 0, 0. So we have second square axis. Okay. S3, this one, okay, is almost the same with the S2, 0, 1, 0, minus H1, 0, and this rotational movement will make the will make the g directional linear motion, is right? Okay, if you make the rotational motion, and then this base origin will going up. Okay, so the magnitude is the L1. So we have this square axis. Okay, let's S4. Okay, S4. S4 axis is aligned to the S3, so 0, 0, 1, 0, and we'll make the linear movement. It's almost same with the S3, so minus H1, 0, L1 plus L2. S5. S5 is aligned to the z-axis. I'm sorry, the going down, so minus z-axis, so 0, 0, minus 1. Okay, because the S5 is up here like this. Let's apply the rotational movement of this element at that time. Okay, we'll make the linear movement of the y directional movement, and okay, let's make rotational movement, and then okay, going down. So one more, the origin has the two directional linear movement with the magnitude L1 plus L2, and in this case the W1 deviation exists, so we have the minus x directional movement. So we have minus W1, 0, the L1 plus L2 in the y direction, and the 0. So we have this. And last one, S6. Okay, S6 is aligned to the S3 and the S4. So 0, 1, 0. And then it will make the linear movement of the origin in the direction of G direction with the magnitude of G in the magnitude of L1 plus L2, and the plus x direction linear velocity appear as well with the magnitude h1 minus h2 minus h1. Okay, so we have the last element. It's a little bit difficult to read the configuration of all the axes. I think you can get many pictures about the UR5 from the website. So by turning around the robot, you can check the distance and the orientation and the configuration. Okay, then as you know, this is the board kinematics. Okay, so the first angle is assigned to 0. Second is the minus 90 degree. This is 0, 0, plus 90 degree, and this is 0. Actually, E2 0 will be the 4x4 identity matrix. So the second and the fifth term exist. Remaining terms will be disappeared. Okay, we have this finite form of transformation matrix. Here, E2 S theta is equal to E2 omega theta G theta V and 0, 0, 0, and 1. Do you remember this formula? How about the G omega, E2 omega theta? According to the Rodriguez formula, I minus I plus sine theta omega plus 1 minus cosine theta omega square. The G theta will be the theta I plus 1 minus cosine theta omega plus theta minus sine theta omega square. Okay, and then the V vector will be applied to the G, then we can get the linear displacement of the homogeneous transform. Anyway, we know the S2 and the theta 2 and S5 and theta 5, then calculate these two components, we can get the homogeneous transform. So by multiplying the three homogeneous transform, then we have it. So we should understand this matrix. Okay, the minus 90 degree movement will make the robot upright like this. And one more, the 90 degree of the theta 5 is applied, then this is also upright. So we have this configuration. Let's lay. Okay, the x-axis is aligned to plus y. Okay, the y-axis is aligned to minus x. So we have this one. The g-axis will be aligned to same g. So we have this one. And then by leading this position, then we have the three displacement in terms of base frame. Like this, we can get the posture, orientation, and position of an defector frame. Till now, we have dealt with many kinds of example with respect to body form, space form of a POE. Okay, now we will suggest another form. It is called as body form of POE. Okay, maybe you know in chapter 2 we have talked about the matrix identity. Any matrix can be decomposed using the as a similarity transformation, and then let's apply the exponential transform. Then we have this equation, is it right? At that time, this m going down, m minus m inverse going down, this m can be going down, so we can write down this equation. It was proved in the chapter 2 front part. So from here, let's multiply m matrix in front side here and here, m and m. Okay, then we have this matrix identity. Okay, we will use it later. Okay, for the kinematics form, in detail, it is space form of POE. Okay, let's consider the last rightmost term here. It is corresponding to this matrix, is it right? So we can change this kind of form from here. So we have this matrix equation. Okay, one more. If you consider this matrix equation, we can get this kind of form again. So one more identity is applied here. This identity is repeatedly applied, then we can get this matrix form. Okay, the letter M is going to the front side, so we have another form of matrix equation for the kinematics. Okay, for the simplification, let's assign M inverse SIM SOB. Actually, it has a physical meaning. It is the square axis in the body frame, not space frame. Anyway, let's assume B as M inverse SM. So, using this definition, we can write down the very simple equation. It is called as body form of POE. Okay. Actually, the S square axis in the space form can be changed into the body form of a square axis using the similarity transformation. In this case, this matrix belongs to R 4x4, but it can be changed by using the adjoint map. Do you remember that? Adjoint map belongs to R 6 times 6. In this case, square axis can be changed directly from the 6-dimensional vector to the another 6-dimensional vector. Okay. M is given by the rotation and the P and the 0, 0, 0 as 1. Maybe the M inverse will be R transpose. How about that? Minus R transpose P 0, 0, 0 and 1. Okay. The adjoint map of M will be the R0 3 times 3 P skew symmetry form of the matrix and the R and the R. Adjoint M inverse will be R transpose 0, same 3 by 3 zeros appear here, minus R transpose and P, R transpose. Okay, so this kind of inverse map of a joint is used to change from the space to the body joint. Okay, above equation, this one, is the alternative form of a POE representing the joint axis as a screw axis BI in the body frame. Okay, robot is at zero position. Okay, let's summarize the two forms. Space form and the body form. Space form, the M appear the last term of homogeneous transformation. M is first transformed by the light digital joint, and then progressively moving inward to more proximal joint. On the other hand, the body form, the M is first transformed by the pulse joint, and then going outward to more distal joint. Okay. Actually, the fixed space form representation of the square axis for more proximal near the base joint, the base frame, is not affected by the joint displacement at the distal joint near the body joint, body frame. Okay, the contrary concept will appear in the body frame. Okay, the relationship between the square axis, it BW implies the between axis of space and the square axis of the body frame. It can be changed using the similar transformation, using the 4x4 matrix. On the other hand, it can be changed using the adjoint map between the twist and between the square axis. Okay, we have the let's have the similar example. Okay, 1, 2, 3. Okay, here. Okay, we have the same and the position represented by the 4x4 matrix. And as mentioned before, this is the body form of POE. M is given here. Okay, the remaining task is to finding out the square axis in the body frame. Okay, the pulse joint is here. Will be denoted by the S1, B1. Okay, the rotation axis is the G axis, so 0, 0, 1 in the body frame. Okay, here. Okay, let's make the movement like this. At that time, minus x-axis x directional movement will appear in the body frame with the magnitude of the 3L, so minus 3L, 0, 0. So we have the first body square axis of the body frame. How about the second one? Second one is the B2. Rotational axis will be the y-axis, so 0, 1, 0, because this is aligned to the B. But there is no linear movement because this line going through the origin. Okay, B3. B3 is this one. So this is corresponding to the minus x, so minus 1, 0, 0. This movement will make the minus g directional linear motion, so 0, 0, minus 3L. Okay, so we have this one. Like this, we have the square axis in the body form. Okay, this is almost end part of this chapter. The WAM is made by the Barrett technology. It has the 7 degree of freedom. Actually, joint 1 is aligned to G, and joint 2 y-axis, and joint 3 the g-axis. The elbow is aligned to the y, and G, Y, G. So it's very easy to read the end position. The orientation is the same. Just the G direction linear movement will be the L1 plus L2 plus L3. So we have this one. Okay. In order to apply the body form of POE, okay, the B1. Okay, let's read the B1. B1 join 1 is aligned to the g-axis, so 0, 0, 1. Okay, let's make the movement g-axis. Okay, this axis rotational motion will not have any linear motion of this part, so 0, 0, 0. Okay, B2 is aligned to y-axis, so 0, 1, 0. Okay, this movement will make the plus x direction linear motion at the body plane. So magnitude will be the L1 plus L2 plus L3. So L1, L2, L3, 0, 0. So we have the second square axis. Like this, we have the square axis in the body plane. Okay, so if you apply the 7 joint angle like this, then we can calculate the homogeneous transformation. So this is the initial post. This is the final posture using this kind of joint angle. So in here, x-axis is written by g. Okay, you right? The y-axis will be the going out of phase. Out of phase is aligned to the y, so the y-axis. The g-axis is aligned to minus x, so we have minus 1, 0, 0. Okay, if you lead the z and x, so we have the linear displacement. It is corresponding to the kinematics of the one. Okay, my pencil is running out. The battery is running out, so okay. Maybe this is the third homework for the chapter 4. Please solve 9 exercise until next Thursday. Upload it as a PDF form or email me. Okay, the due date is given, but if you don't have much time to solve this exercise at that time, please email me including the PDF file as a homework. After due, I will allow it. Okay. Okay. One more. If you have some question about this exercise, then let me know that. I will try to represent a solving procedure if you give it to me until April 14th, Tuesday, next Tuesday. Okay. I'll try to show how to solve it next time. One more, maybe next Thursday we will have real-time lecture. Okay. Now I finished the chapter 4, but we don't have much time to solve exercise. So next Thursday morning, maybe 9 a.m., we will have Zoom meeting. I will stand in front of the blackboard. So if you ask me, I will try to write down the solving procedure in the blackboard. Okay, thank you for your attention. See you.